Imagine that you're flying through space, when suddenly you start to get dragged toward a dark abyss. Reality as you know it starts to change. Time begins to warp, and
so you start to feel this strange sensation of being stretched.
You're falling into a black hole, one of the most astonishing places in our universe. Some are so big that they can fit over 60 of our solar systems across them, with masses up to 100 billion times our sun. And once you fall past a certain point, nothing can escape. Or can it? I wanted to know the latest cutting-edge research about black holes, so I called up my favorite physicist, Dr. Brian Cox, to answer the question, if you fell into a black hole, what would actually happen to you? What would it feel like? And what does our newest science tell us is really happening inside a black hole?
Black holes? One of the strangest things in existence.
A mathematical enigma.
You come face to face with the structure of space and time.
Now let me leave, man. Spaghettification.
Black holes ain't so black.
Nature doesn't work that way.
It's the most wonderful thing.
It's incredible. Imagine that you and I are on a mission to fall into a black hole, and we have some imaginary spaceship that can take us as far and as fast as we want. So we get into our spaceship. What now? What is a black hole, and how do we find them?
So essentially, what's the idea behind a black hole? Let's say you take the sun, a star the mass of the sun, and you just collapse it, and you keep on collapsing it, and you squash it down, and you squash it until its radius becomes 3 kilometers. 3.
If you artificially squashed all of that mass into that tiny little space, the gravity right at its surface would be immense. So immense that if you wanted to escape,
the speed you'd have to travel to escape its gravitational pull, it's called the escape velocity, would exceed the speed of light. So even light rays emitted from the surface, if you could squash it down that far, would just stay there.
That is a black hole, a spot so massive, with gravity so strong that not even light can escape. At first, black holes were just a mathematical quirk, a weird solution to equations that seemed to otherwise fit our universe. They were only theoretical, but then we started to find them. Over decades, scientists measured the movement of stars and galaxies and gases that were warped by seemingly empty patches of space, left behind, we now know, by the collapsing death of stars much larger than our sun. We discovered that black holes are real. We can now tell they're all over our universe. Some estimates say there are up to 40 quintillion of them. And almost every galaxy has a supermassive black hole at its center, including our own Milky Way. Let's go. Let's imagine that we choose the black hole at the center of our own galaxy.
Yeah.
Sagittarius A star, I think it's called. I know that we took this picture of it. What are we looking at here?
So here, the light, you might say, what is the light in this picture? So it's not from the black hole, because as we've just said, black holes trap light. It's from what's called the accretion disk.
This is another way that scientists have found black holes, by spotting their glowing accretion disks.
So you're to imagine really material spiraling around in orbit, around this very dense object, and very violently orbiting. And so it heats up and it emits light.
Wait. So then why in this photo do we not see the accretion disk across the middle? Well, it turns out that we happen to be seeing this particular black hole from above. But if you were to see it from edge on, something very weird starts to happen. What we're seeing is actually the accretion disk in front of and behind the black hole. Because the black hole's gravity is so immense, it's causing light to be bent and distorted around it.
So imagine this disk of material around this thing. Then light rays, let's say from your perspective, from behind the black hole, go around into your eyes. Sometimes they orbit and then go around into your eyes. And they go into your eyes from every point on the disk, from underneath and at the top and behind. So you have light rays going always around this thing. So you see that. That's what you see as an image.
And in our little spaceship, we're getting closer. As we approach, I start to wonder, how big is this thing? Based on the way it pulls at the stars around it, scientists estimate that the black hole at the center of our galaxy has a mass of 4.3 million times our sun. But if you plopped it down inside our solar system, this black hole would only extend to about 1/5 of Mercury's average orbit. So it's shockingly small for its immense mass. And compared to other black holes, ours is just medium. One of the smallest black holes ever found is J1650. Its diameter is only about as long as Manhattan, but it has a mass of 3.8 times our sun. One step up would be the black hole in Messier 15. It's about twice the diameter of Earth, with a mass of 4,000 suns. Okay, now we're at the lower limit of what's considered a supermassive black hole. This one is just under half the diameter of our sun, but about 100,000 times its mass. And here's Sagittarius A star. Now to the truly insane. The black hole in the galaxy M87 weighs 5.4 billion suns. You could fit our solar system around 4 times across it. It was the first one we ever got a picture of in 2019. And this is one of the largest black holes ever discovered, Ton 618. It weighs 66 billion times more than our sun, and it could fit nearly 40 of our solar systems across it. But it might not be the biggest. Phoenix A seems to have a mass of 100 billion suns. But since this black hole is closer, we're seeing what it looks like more recently than Ton 618, which might have grown since. And these are just the biggest ones we know of. There could be an even more massive one, just waiting to be found. And now, we're starting to get pulled into one.
So we're falling towards this thing now, and we turn our rocket motors off. We're just in free fall. We're just floating. So it's like the astronauts on the International Space Station. We're just there. So we could be approaching this in this room now, and we would have no clue that's what's happening.
What about when we're in the accretion disk? Wouldn't we be banged around by a lot of stuff?
We might get in a bit of a mess as we fell through the accretion disk. You're absolutely right. It's a bit nasty around these things. But let's say that our room, this spacecraft, is magically insulated from radiation and heat and all those things. Then, nothing. One of the most shocking things, from the point of view of someone outside, the description is very different.
Okay, now imagine you, yes, you, watching this. You go outside and you look with an all-powerful telescope at me and Brian falling into this black hole 26,000 light years away.
So what would they see happening to us as we fall towards this thing, as we approach the black hole? If they could see our watches, they would see our time tick more slowly, more slowly, more slowly, and they would see our time stop on the horizon.
Stop, this is incredibly important. As we get closer to the black hole, there are now actually 2 journeys. There's our journey as we see it, and then there's our journey as you would see it from far away. And they are very different. Why? Because black holes are distorting space and time near them.
And that's absolutely central. There's nothing weird. Well, there's something weird there, but there isn't, according to Einstein.
Albert Einstein was the one who realized that space and time are actually one thing, space-time. And space-time is stretchy.
Space-time responds, warps or curves, to matter and energy in the universe. The theory that Einstein published will say, give me like a ball of matter, and the equations will tell you how the fabric of the universe is distorted.
A black hole is the most extreme example of this distortion that we know about. The math tells us that reality very close to it and very far from it are not the same. So it looks to us like the universe is speeding up, and it looks to you like we're moving in slow motion. Now we're crossing the line where no light can ever escape to reach you again. For us, we don't feel that. But for you, you never actually see us cross it at all.
They would never see us fall in. From the point of view of someone outside, nothing goes into the black hole, ever.
Do they see us imprinted there forever, or does the light from us slowly fade until...
This light is climbing away through this gravitational field, so it's getting stretched. So we get redder and redder and redder, infinitely redshifted.
And from our perspective, there's no turning back.
You can write the equations as a space being like a river that flows into this thing, almost like a sinkhole or something in space. And the river of space flows at the speed of light inwards on the horizon, and then faster than light inside. So if you imagine that you're a photon, a particle of light, you're like a little fish swimming against the tide. But if the tide's going at the speed as fast as you can swim, the speed of light, you can't get out.
We're now past the event horizon. But before I show you what's inside this black hole,
Let me show you something here on Earth. I'm finally building Huge of True's first website, and I'm really excited about it. The reason why I think we need one is that we obviously have our home on YouTube, but we need some place to tell you about the show, about different things that we're doing, and maybe sell some merch very soon. Wait, I think I have a sneak peek. Yeah, you'll see me wearing this a lot. And it's got this cool if true on there. And I can build our site with Hostinger, our sponsor. I just clicked here. I got a business plan, which has a bunch of cool features, including an AI logo maker, if you're looking to just brainstorm ideas. And of course, if you're looking to sell something, it has e-commerce features. And I just start building. I'm using their AI website builder, which is fun. It can even write copy that's very good for SEO, which makes things easier. If you want to build your own site, I've really been enjoying using Hostinger, and I think you might too. And right now, they're offering you, the Huge Crew, 10% off if you use the coupon code CLEO. Make sure you use it if you sign up, because that helps this channel. Seriously, big thank you to Hostinger for supporting us and optimistic, independent journalism. Now, let me take you inside a black hole. We're past the event horizon, but we're still falling and falling. And finally, we begin to feel something. Gravity is increasing faster and faster. And this is where we get to maybe my favorite word that I have learned in the process of this. My understanding of this is when the gravity at your feet is so different from the gravity at your head that you begin to stretch in a very dramatic way. And this is spaghettification.
Yeah.
Could you explain what is happening here?
Yeah. Another way of thinking about it is just that the distortion in space-time is not constant over the length of your body. It's not only stretching, it's also a squashing. You start to feel this strange sensation of being stretched and squashed. And as you go closer and closer to the singularity, those effects become much more extreme, until they're so extreme that, first of all, you cease to stay together.
We're one long string of atoms?
Yeah,
Well, what are we now?
And then the atoms get separated, and then the protons, the quarks inside the protons will get separated, and ultimately everything is gone. Everything's been ripped apart.
And all the ripped apart pieces that used to be us are still racing inward toward the singularity.
I think it's really tempting to picture it as some infinitely dense point to which this star collapsed.
But since a black hole is a distortion of space-time, the singularity is not just a place, it's also a
Moment in time. And it's in fact the end of time in Einstein's theory. Then it's really beautiful because you think it becomes something that's in the future for anyone or anything that crosses the horizon. So it's like if you say, well, I want to escape this thing, it's like saying, I want to escape tomorrow. If I said to you, let's run away from tomorrow, you go, I can't run away from tomorrow, it's in the future. That's what this thing behaves like, singularity.
If imagining the center of a black hole as the end of time feels like your brain is getting spaghettified, that's okay. But it's about to get weirder.
So we have passed through the event horizon, we have been spaghettified, we have hit the end of time. The question is, can we ever get back out?
So the answer is, according to Einstein's theory, no. Einstein would say it's all over. You've got ripped to bits. You've gone to this infinitely distorted space and time, and it's just done.
What would Stephen Hawking say?
In his words, he discovered that black holes ain't so black.
Stephen Hawking discovered that black holes, which according to Einstein's math, nothing should ever escape and they should only live and grow forever as they just suck in mass around them, something actually does get away.
What's called Hawking radiation is emitted from the black hole. So that what is that? What particles being emitted? It's a temperature. It's glowing. And so that means it's losing energy. And so that means it has a lifetime. And that means one day it will be gone and space will be all nice and normal again, right? All you will have left will be the Hawking radiation that's been emitted over these eons of time.
Okay, I think something is missing from my understanding of the universe.
Yeah. I agree with you. Something's missing in my understanding as well, and everybody else's. But
Here's what I think is missing from mine right now.
Yeah.
So all of this matter has, including us, passed through the event horizon, ended up at the singularity. It is something in there.
Yeah.
At the end of time. And also, I know that every law that we have about the universe says that information is conserved. If a black hole will one day end up as nothing, what happened to you and me? What happened to all of that stuff?
I mean, this is the central question. So Stephen's initial calculation was the Hawking radiation is information-free, purely thermal. So that would suggest, as you said, that the information, any record of anything that fell in, will have been erased. That is weird. The laws of nature are quite clear on this. Information does not get destroyed in the universe. It gets scrambled, but it doesn't get destroyed. So that's what bothered everybody.
What happened? What's the end of the story?
So what happens?
Answer the question?
So the end of the story, we're not at the end of the story yet, but in 2019, a series of papers were published. Those papers suggest that Stephen missed a bit in his calculation, very subtle. But it turns out that the radiation is not information free. At the end of the process, then all the information about everything that fell in is imprinted in the radiation, as you would normally expect.
On the one hand, that makes sense, because then the information is not destroyed. But on the other hand, that's even weirder. Because how then did the information, which went to the singularity and the end of time, and get outside again as radiation?
But you say, well, what's the picture then? What happened? Because I understand if I take this and throw it into the black hole, it's gone across the horizon, it's gone to the singularity. It's definitely true that nothing comes out of the black hole. So how is this information about this thing getting imprinted in the radiation? And I should emphasize the health warning here. This is ongoing research, and there is no agreed upon picture.
This is the cutting edge of research into black holes.
One description of our perspective is, we go to the singularity, we get all scrambled up. And then it looks like the interior of the black hole is in some sense the same place as the exterior. You could almost picture wormholes opening up from the interior of the black hole to the exterior. And very naively, you imagine our bits of information going through the wormholes and coming out again. We end up outside. The information ends up outside in the Hawking radiation. Even as I say this, there are papers being written saying different things. It's really cutting edge stuff.
Different things like, well, maybe you never go in. Maybe there actually is no in of a black hole. Or maybe everything is just information with no real place at all. And now my brain is breaking.
It does look like that there is a description of the universe that looks like a giant quantum computer, which does not imply that someone built it, right? It doesn't imply that we're in a simulation.
Perhaps.
But it does suggest that there's a good description of reality that you can write down in the form of some kind of network of entangled qubits, something like that. And I think it's fair to say that the jury is still out on these issues. But what the thing to emphasize is there's something really fundamental going on here. And it almost certainly is associated with the nature of space and time themselves, or space-time.
Black holes are an incredible gift because they stretch the limits of our understanding of our universe.
We struggle with it, but it's hard for us. You start to come face to face with the structure of space and time.
In their strangeness, their extremeness, black holes reveal the hidden structure of reality that governs everything, including our everyday lives.
You're studying completely collapsed stars, or the things at the hearts of galaxies, and you're gaining insight into quantum computers and networks of qubits and quantum information. It's the most wonderful thing.
It's incredible. One of the things that I really admire about you and your work is that you have this sense of wonder at the universe. You give that sense of wonder back to people. You say, hey, don't you remember what it was like when you were a little kid looking up at the sky? And actually, in fact, as you learn more about the universe, that sense of wonder can increase, not decrease.
Yeah.
And I think that's really special, and I think that people need that. And first, I just wanted to say thank you.
Oh, thank you.
And second, my last question for you is, how do you feel when you go outside and look up at the night sky, given what you know?
The sense of awe and the sense of mystery and beauty increases the more you know about what you're looking at. It doesn't decrease. The number of mysteries increases the more you look at it. So anybody watching this, if it's a clear night, you can go outside